Everybody, welcome to our quiz 5 walkthrough. I'm Maisie. I'm going to be taking you through this quiz. Let's just get started. Okay, so the first question, this week we really got into stereoisomers, right? So our first question is going to talk about stereoisomers and sort of how we determine stereochemical labels like RS and EZ. So this is very important. So let's check it out. So this problem asks you to draw the possible stereoisomers for 4-bromo hex 2-ene. So first things first is I just want to draw a generic version of this before we start adding in the stereochemistry, so we know at least where the bonding is, the configuration and the constitution of this molecule before we move on to the stereoisomerism. So we have a 6-carbon species, 1, 2, 3, 4, 5, 6 carbons. It looks like on the second carbon, we have an alkene. So let's number these guys. 1, 2, 3, 4, 5, 6. So it looks like from the second to the third, we will have an alkene, which will be here. And then on the fourth carbon, we will have a bromine. So our fourth carbon will have a bromine. So now we just have to label sort of where the chirality is in this molecule, which we could have gotten from the name, but it's nice to have a picture as well. So the chirality in this molecule is twofold. Number one, we have what we call a chiral alkene. So an alkene that can be cis or trans, or the more formal way to do it, to call them, is E and Z. And then we also have a chiral center. So we have two different chirality determining elements in this structure that we need to consider. So now let's think about what the different possibilities are. Well, for any given stereocenter, for any given chiral center, we can have two possibilities, right? We can have it be an R or an S. So that's going to be one of the two possibilities. And then if we sort of make a tree diagram, like you learned in math class, in like 6th grade, if you make a tree diagram downwards, we can see that if something is R, if the chiral center is R, then you could have an R alkene with an R chiral center with an E alkene, and you could also have an R chiral center with a Z alkene. And then we can sort of break that down the same way on the other side. So we could have an S chiral center with an E alkene, or an S chiral center with a Z alkene. So those are going to be our 4 possibilities, right? And we could have determined that using our 2 to the n formula. So 2 to the n equals number of stereoisomers total. This is just sort of a more concrete visual way of breaking down that same information. So now let's just draw those possibilities, right? Well, in order to make 2 different chiral centers, I always like to use this little trick. Things that are wedged become dashed when you change them from one absolute configuration to another. So you could have this compound, which we can go back and label the stereochemical label in 1 minute. We could have this one. We could have this one, right? So we've switched the chirality at these 2 centers without touching the alkene. And now we can change the alkene and keep the chiral center the same. So we'll keep the chiral center the same. Oops. I was too hasty. We'll keep the chiral center the same, but we'll change the alkene from trans to cis, or the better way to call it is from E to Z. So this is an E alkene, and then this is a Z alkene. And then we can do a Z alkene with a dashed Br as well. So we also have a Z alkene with a dashed Br. So I'm just going to label these so we remember. So this is E, E, Z, Z. And we would call this Z at the 2 position, Z at the 2 position, E at the 2 position, because the alkene is at the 2 position. So now let's talk a little bit about determining the ranking of these guys. So usually the most interesting thing on the molecule is going to be ranked first, right? The number 1 priority. So the number 1 priority here is going to be our bromine. And then we can move on and try and determine the other priorities. So honestly, once you have done this enough times, you don't have to think so hard about it, but you can kind of just look at it and say, well, this alkene looks more interesting than the alkane that's on the other side. So the alkene is probably going to win. And if you want to compare the number of carbons bonded to carbons and all that stuff, you definitely can. So this carbon is bonded to 1 carbon and 2 hydrogens. So 2 hydrogens here and 1 carbon. Whereas this carbon is bonded to 2 carbons, quote unquote, ghost carbons, and 1 hydrogen. So this side of the molecule, the side with the alkene, is technically more interesting. So therefore would get a higher ranking when you're doing your ranking for chirality. So this would be our 2 priority group. Our 3 priority group is the other side of the chain, and then our hydrogen is pretty much always going to come in last. So let's determine the absolute configuration here. We're going to use my box method. That's not actually mine, it's Morton's, but I love it. So we have R, S, S, R, even in the back, odd in the back, clockwise, and then counterclockwise. So we have an even in the back here, so we're starting in the first column. And then if we look at the other guys, we go 1, 2, 3, counterclockwise. So this guy is S, and this guy will therefore be the opposite. If you don't trust me, you can go ahead and do it yourself, but this will be an odd in the back, so it'll just shift over to the other column. So this one will be R, this one will be R, and this one will be S. So now we have all 4 possibilities drawn out just as easy as that. And so what I would do when I'm approaching a problem like this is just sort of write out the first thing that comes to mind when I think of this so that I can identify the different components. So like I recognize that this is a chiral center and this is a chiral alkene, and those are the parts of this molecule that are going to be important. And then I would just switch them one at a time. So keep the bromine the same and move the alkene. Keep the alkene the same and move the bromine. And then you end up with all 4 of your possibilities. Okay, so let's talk a little bit about question 2 now. So question 2 is asking us for the same information sort of that we figured out for question 1. So we're going to figure out the chirality of the 2 chiral centers that are in this molecule. We can sort of tell that there are 2 chiral centers here because each one of these carbons is bonded to 4 different substituents. So that would be my first step, is to determine where the chiral centers are, and then we can go about determining their absolute configuration. So let's just do some quick labeling here. This is your first priority group. The more interesting stuff is closer to this side. So this is going to be your second priority group. The less interesting stuff is on this side. So this is going to be your third. And then obviously the hydrogen is the least important of all of them. So if we go through this, this is, if we can use my box trick again, should have copy and pasted it, but didn't. R, S, S, R, even, odd, clockwise, counterclockwise. So we have an odd in the back, so second column, and we have, let's see, 2, 3, 4 clockwise. So this top chiral center is going to be S. I'm just going to erase all of this stuff so that we can do it again on the bottom. So this one is S. And then if we do this again on the bottom, this is our first priority group, fourth priority group. More interesting stuff is this way. So this will be second. And less interesting stuff is this way. So this will be third. And if we do that, we have our, I gotta get rid of that arrow, there we go. We have our even in the back, so first column, and then 1, 2, 3, we have counterclockwise, which is going to give us S. So both of these chiral centers are S in our starting material. So now we're going to transfer this stuff onto chair conformers. But first, before I do that, the second or the third part of this question asks about creating the enantiomer of this guy. So I would rather do that first, and then we can show how the enantiomers transform onto the chair outlines. So the enantiomer, right, we know the best way, or I think the easiest way to switch chirality, to switch absolute configuration, is to just change whatever is dashed to wedged and wedged to dashed. So that's all we're going to do here. We're just going to change the fluorine, which was dashed to wedged, sorry. And then we're going to change the tert-butyl that was wedged to dashed. Should try saying that a bunch of times fast. It's not easy. So this is actually going to be our enantiomer with absolute configurations of R and R. If you don't believe me, just do the ranking yourself, but we switched both chiral centers, so it should work. So now we have 1, 2, 3. I'm going to label those carbons as 1, 2, 3, and these ones are still 1, 2, 3, even though it's the enantiomer. So the way that I would transfer the information onto these guys, the really important thing about these structures is that this tert-butyl group is something called a locking group. So it will prevent it will only exist on a ring in an equatorial conformation. So the tert butyl can never be axial. So we have to work out a way of showing that it can never be axial on the structure, on the chair structure outline that we've been given. So I'm just going to arbitrarily pick, well, it's going to look arbitrary, but it's not actually arbitrary. Because on an up carbon, right, an up carbon is one with arrows. If you were to make the arrowhead look like this, so these three are up carbons. On an up carbon, the up position is axial. So we're going to want to put this tert butyl on a down carbon because we don't want it to be axial. We want it to be equatorial. So I'm going to put it on this carbon. I'm going to make this carbon carbon 3. And it's up on a down carbon, which means it's equatorial. So we have a T-but here. And then we can also have our fluorine that's down. So this is a down carbon, which means the down position is axial. So on that down carbon, this is 3, 2, and then 1 is right here. So because that fluorine is down on carbon 1, dashed means into the page, which is down, wedged means out of the page, which is up. So this fluorine ends up being axial. Not the best, but also not the worst, because fluorine is really, really small. So it doesn't really care that much about being axial compared to the tert butyl, which is enormous, even though it's not drawn to scale here. So now we got to create the enantiomer, right? We got to draw the enantiomer that I drew in the planar structure. So now we want this tert butyl to be on an up carbon, because if we leave it on a down carbon, the tert butyl will be down, which is the axial position, so that's not what we want. So we are going to put it on an up carbon. So I'm just going to put it here. So we just shifted everything over 1. So this is 3. 2 will be the down carbon in the middle, and then 1 will be fluorine is up on carbon 1, just like this. And you can sort of see the symmetry here. So if I were to take this, it's sort of a difficult thing to draw, but if I were to take this chair, which we still remember is a circular structure, if I were to take this chair and sort of rotate it a little bit, like I was putting it on a plate and spinning it, you would sort of be able to see, right, that this carbon matches up with this carbon matches up with this carbon, and this carbon matches up with this carbon. And it looks like a mirror image. It does when you rotate it around. This is a great exercise for your model kit. But because it looks like a mirror image, we could probably trust that it is. I mean, of course, you can check the absolute configuration in the chair conformer if you want, but I'm just going to trust that we've correctly drawn the enantiomer. So this is the lower energy conformer of the enantiomer, and this is the OG structure. Okay, so let's move on to question 3. So I've set up all of these pairs that are in question 3, and we can talk about sort of how to arrive at their relationships. So this first one, I think, is a great example because I really think you have to convert things they give you in different formats into the same format. So there's, like, for example, this is a sawhorse, and this is a Newman. I would put them both in Newman or both in sawhorse. So why don't we do this both in Newman? So I'm just going to take this guy, and we're going to make it into a Newman projection. So this back carbon will be this one. This front carbon will be this one. And we will have a Newman that looks very similar to the one that the other material they give you. So if we have turned it so that we're looking down this axis, downwards, right, our eye is right here, downwards is going to be a methyl. Out and to the right is going to be a chlorine on the front carbon. Up is going to be a methyl. Into the page and to the right, or to the left, sorry, is going to be a hydrogen. So the hydrogen that's back here is this guy. And the chlorine that's in the front here is this guy. And then the other two are just hydrogens. So right away, you should be able to tell that there's something wonky going on here. We don't have an ethyl in our second Newman projection, and it wouldn't have worked out to be an ethyl if we had looked down the bond this way as well. The chlorine is still on the front carbon, but that's pretty much the only similarity. So it's pretty safe to assume at this point that these guys are going to be constitutional isomers. And you'll see that if you turn them into a sawhorse, because you'll see that the bonding is completely different. The chlorine is on the middle carbon of a longer chain in the second structure, as opposed to in the first structure, where it's on the very front carbon of a long chain. So that is our first one. Now let's talk about the second one. So this one is also going to be important to convert to two things that are similar. Let's make this one a sawhorse this time. We'll do it the opposite way. So for making this a sawhorse, I always like to start with looking at things that are anti. So the things that are anti in this structure are 2 methyls, 2 chlorines, and 2 hydrogens. So I'm just going to go ahead and make the chlorines the things, actually I'll make the methyls the things that are anti, because these methyls are anti, right? So it's good to start with things that match up between the two structures if you're trying to determine if they're the same. So the methyls look like this. We have a methyl here and a methyl here. And I'm going to say, sorry. I'm going to say that, actually I should do it this way. That makes more sense. So we have this methyl is this guy, and we have this methyl in the oval is this guy. So now we have to put the chlorines trans to each other, anti to each other. So I would do that by making one of them wedged and one of them dashed. And then finally, the same thing with the hydrogens, one of them wedged and one of them dashed, which would make them anti to each other in our sawhorse. So now let's take a look and do a comparison here between these two structures. I'm going to move our Newman projection out of the way so we can compare these two structures now. And I'm going to erase some stuff just to make them look fairly similar. So we know that these methyls are there, that are just the straight lines in our stick formation. And then the hydrogens we also know are back there, so we don't need them drawn. And just so that, even so our methyls line up perfectly, I'll do a pancake flip here and have the methyls look like this. And then the chlorine on the front carbon would be in, and the chlorine on the back carbon would be out. So we can tell now, after we've done all of that elimination, or all of that manipulation, is that one of these chiral centers is the same. So the one on the front carbon is the same between these two structures. But the one on the back carbon is different, which is going to make these diastereomers. So these two are diastereomers. So first one is constitutional, second one's diastereomers. So hopefully you're starting to see the importance of switching to compatible so that you're looking at the same type of structure in both instances. Let's talk about the next pair. This one is actually going to be super straightforward. It looks very similar right now, and it looks like you should even just be able to spin it and it should look the same. Let's do a pancake flip and find out. So I'm just going to pancake flip so you can see how I like to think the top of the house on the cyclopentane is sort of right here on this one. So if I flip it over this line, we should get something that looks pretty similar to the thing that we're trying to do, or the thing we're trying to get to. So let's look at that. So if I do that pancake flip and flip it just like this over the line, and then our little hat is right here. So the chlorine is on the left side of the hat, but it was going into the board before, which means it's coming out now. So it's wedged. And then the bromine is the opposite. So the bromine is going into the page instead of out. Because if you think about it like a pancake flip, right? If the bromine was coming out at you and then you flip it over, it would now be going into the page. So now we can look at this very similarly to how we looked at the first one and say, well, this chiral center got changed and this chiral center got changed. So therefore, these are enantiomers. Very good. We're checking all of our boxes here. We're going through all of the different relationships. This is great. Okay, it looks like I made a mistake copying this one because I accidentally drew the same thing twice, and that would be just too easy, wouldn't it? So let's look at this one. So this one has the other structure, looks like this. So, perfect. So this one is one where you really have to be careful because in reality, this thing does not have any chiral centers. And you would think at first, this looks like a chiral center. What do you mean? But look very carefully. This is a methyl, and this is a methyl. This is a methyl, and this is a methyl, which means that this carbon is not bonded to 4 different things. It's not a chiral center. So that's a really important distinction, because if it was a chiral center, this would be an enantiomer. But because that's not a chiral center, this is not going to be an enantiomer. So let's just pancake flip, because what we can do here is actually just pancake flip this guy so that we get the long chain to match up. So we pancake flipped, and now that methyl is going into the page. And you would think, again, be careful because this is wedged and this is datched and we flipped it, so why wouldn't it be the enantiomer? Because that's not a chiral center. And in order for something to be an enantiomer, it has to have a chiral center, at least one. So all you have to do is grab this propyl group, this guy right here, is grab it like a doorknob and spin it so that one of the methyls comes forward, or so that the one of them is in the plane and one of them is forward. So all you have to do is rotate around this bond just in one circle like you're twisting a doorknob, and you will eventually get to something that looks like this. So in reality, they are the same compound in a different conformation. So these two are conformers. Very good. Okay, and now let's get to the end here. We have two more left. So let's look at this one at first. This one honestly should just scream out to you, because in here the oxygen is double bonded to a carbon and does not have a hydrogen on it. In this one, the oxygen is single bonded to a carbon and has a hydrogen on it. So automatically the bonding is different. So this is not going to be any type of stereoisomer or conformer. It has to be a constitutional isomer. Just like our first example, the bonding is physically different, so that makes it a constitutional isomer. So these are also constitutional isomers. And like we've learned about at this point, these are constitutional isomers that result from tautomerization, which is a fun little connection here. And then last but not least, we have an octene, which is kind of a fun molecule. Octene is pretty much the smallest ring you can go and still be able to make a trans alkene in a ring. Once you get small, I think you can actually do it with septane too, but, or sorry, I guess it's heptane technically. But yeah, so it's really hard to get a ring to conform such that you could put a trans alkene in it instead of a cis alkene. But this is one that can do that. So like I sort of alluded to there, this is an this is a Z alkene, right? It's cis, because the more interesting things are on the same side. And this is a trans or an E alkene. And so what do we call the relationship between a Z alkene and an E alkene? Those are just diastereomers. So this pair, diastereomers. I do chemistry, not spelling. Okay, so when we have a Z alkene and an E alkene, and that's the only difference between two molecules, then we have diastereomers. So those are all of the relationships between each of those things. Sorry, I kind of went through them a little quickly. I just don't want this video to run too long. But anyway, that should be all of it. And if you have any other questions, don't hesitate to email me or reach out on Piazza. All right, have a great day.